if they're here, for taking interest in listening to this. My name's right there. I say Lapyre, but you can say it different ways depending on where you are. So I want to talk about, this would be a little word, symbolic computation in computer algebra. And the first thing I want to talk about is what that might mean, because sometimes it's a bit fuzzy what people mean when they say that, and it can mean different things. And you'll see debates in online forums about, what's the best thing to use? I want some computer algebra. Well, use this, we'll use that. It's great, this thing is fast. But, like a lot of things, a lot of pieces of software, it's complicated, and they do different things, and you want to choose the best thing. So I'm thinking sort of a symbolic computation and computer algebra is two slightly different things. And I'm going to draw a didactic dichotomy here. So things aren't really always such polar opposites, as I'm going to say here, but it gives you a framework for understanding what these two kinds of things are. And I don't think you have a meter stick, do you? That's all right. Maybe this thing? Yeah. So, and I'm going to use two Julia packages to illustrate this briefly. Abstract Algebra is a package that's out there right now that I think runs on 0.7. And for the people who wrote Abstract Algebra who might want to use it, algebra or computer algebra is what an algebraist does. And that's a species of mathematician. And they're concerned with rings and homologies and algebraic structures and objects within them. So the people who do this computationally go by different names and so forth. This, if you look at these slides later, these are live links, and this is a stack exchange debate on what an algebraist is. So these are not symbolic programs. At the 0th order level, they're not symbolic. They're organized around types, so language types, I mean like Julia data type, that represent algebraic structures. And they're optimized for numeric efficiency above being flexible. And typically discrete numeric efficiency. So you'll be representing some objects or some algebraic structure objects within that using discrete things like integers. And the leader, the best, sort of the most widely used indispensable program that people who want to publish papers using this sort of thing is called Magma, which started in 1993. It's proprietary. It's cited in a lot of publications, and people have put some effort into finding a way around using Magma for the typical reasons that people want OSS solutions to things. Okay, and so Samata, which is the package I wrote, which I'll be talking about quite a bit today, but not exclusively. I sort of thought, a lot of the things people are talking about at this Julia conference are, at least in general, people know the basics of the background of what you're talking about, but I thought it would be more interesting to people to get a little bit of a broader view. So I will talk quite a bit about Samata, but also about computer algebra and symbolic computation. So what I think about, and what a lot of people think about, if you're a geologist or a biologist or a physicist, is computer algebra is a tool for a scientist or engineer to plow through some calculations quickly so they can check their calculation and get their paper out and stuff like that. And they don't care what what algebraic structure the symbols they're typing belong to or whatever. They want an answer and they want their paper. So these are very different things. These tend to be symbolic, very symbolic. They want to do algebra, calculus, etc., and numbers. The organization, and this sort of gelled decades ago, is around expressions, which are similar to a Julia expression. Types are much less important. It's quite flat. So, for instance, there's a few types. You'll have integers, maybe floating point numbers, and symbols play a big role. So symbols can represent a wide variety of these sorts of things that people use specific types for, and it's very mutable. I can start with an expression that I get some way and say, well, now for the next step, I really want to interpret this some other way. And I don't want to convert it, I just simply want to use it that way. That sounds inefficient perhaps, and it is. They're optimized for flexibility before efficiency, and system integration. System meaning the rest of the symbolic stuff you have to do, and perhaps the numeric system. I want to be able to move stuff around quickly without thinking like a programmer. I've met people who are good scientists who don't realize that Mathematica is a computer language. They think it's a super calculator, which it is to a certain extent. So the leader here is Mathematica, which is also proprietary and is cited a lot. And this is interesting. I mean, NumPy is competitive with MATLAB, has been for some time. Julia is competitive. People have written stuff in C++ to do their numerics. There's really nothing close to Magma in Mathematica. You know, maybe Maple for these kinds of things. That's a question I'll get back to. So here's an example of a Samata function, which is actually, and this is the same as a Mathematica function, just the symbols for the notation are slightly different. You trade a curly bracket for a square bracket, and it's Mathematica, and a couple other things. And they're actually organized as replace. This is not really a function, but one of a set of rules which are tried in order to see if something matches this argument, and then you do the replacement on the right. And one nice thing is you can tell beginners that this is a function, and they'll use the word function, and that's good enough. But it's actually a rule replacement thing. And what this does is say, give me, so an expression is always a head, like a Julia expression, and then a sequence of arguments or elements. And all expressions have that form, except for the atomic ones, like a string or an integer. And this says, okay, match a head, and label it F, and then these two underscores here say match all of the arguments and label them args. And the way I followed Mathematica's convention of sort of automatically splatting this, when I use args on this side, it's splatted by itself. So if you want to collect it, you have to put a list constructor around that. But what this does is take the last element of args and put it in front, and then put the head in first on the list, and most says take the rest of the args and put them there. And this is called rote head args, and it constructs, this is a plus b plus c plus g of x, which you write in full is plus the operator with all these things as arguments, and this is the expression it constructs. Okay? And this is not something you even want to think about up here. Is this meaningful or not? A sort of a thing people figured out a long time ago with Maxim and Mathematica is not to second guess the user and say, let's not support this because I can't think of a use for it right now. You want to allow the user to do this in case it's useful. But you can see what I've done. Plus is, now that it's an argument, it's no longer output this way. It's rendered as the operator plus. And this is nothing efficient. This is a symbol. And I've chosen for the moment to actually represent these via Julia symbols, although sometimes people want to take one step back. Okay, and then I need to get my timer out. I'm going to have to skip things because when I was going through this, I realized I'm going to have to skip some things. Okay, so I want people to be interested a little bit in this talk, so let's do some benchmarks. This is a test that Richard Feynman came up with a long time ago. It's a Feynman-like test. You'll put different numbers in here, but it's a test for how efficient things are at polynomial manipulation. And one interesting thing is, although I said there's this dichotomy, and in fact, actually, those are sort of two poles, and you'll find programs or libraries all along the axis with those two poles at the edge. But one thing all of them will do is polynomial arithmetic. So this is a multivariate polynomial, and this is the way Feynman always sets it up. You take f, and this is a multivariate polynomial in 3 variables, x, y, and z. Depending on which language you're using, you either have to explicitly say that, or it will be implicit just by only using 3 symbols. And then you raise that to some power, here 20, to get good timing. And this, in all of these systems, doesn't take any time to do this. And I want to expand it. I want to expand it all so that this system is representing internally all of the exponents, and all of the coefficients. And then this is the part that's slow. You add 1 to this polynomial and multiply it by itself. So I tested some existing things. Abstract algebra, which is written in pure Julia, does this and gets all the coefficients and exponents in 0.19 seconds. Pari, or I don't know how you say this, does it in 1.5. This is also what a numerical algebra researcher who does this for a living found, but I looked a little closer, and this is erroneous. This thing is not actually expanding it. It's putting it into an intermediate form, and I could not find out how to make Pari expand it, so I should really scratch this one out, but you'll see that some places it's not right. SymEngine is the Julia wrapper to a C++ library that the SymPy people want to use to replace SymPy, which until now has been pure Python. And that did it in 3.8 seconds. And an interesting thing here is there was no information about the ring or field or what sorts of objects I was going to use. I'm not sure what SymEngine supports at this point, so I'm not sure. There's 15 left. Okay, thank you. I'm not sure what it supports, so I'm not sure what it is. Mathematica 3 does it in 7.7 seconds, and I'm pretty sure if you tweak this problem very slightly, it takes an eternity to do. So this is a typical mathematical thing. It's a very general program, and they use some heuristics and expert stuff to try and say, this is a multivariate polynomial. I'm going to convert it to another form, do the calculation, and convert it back. And you can reverse engineer Mathematica a bit to find out that that's actually what's happening. SymPy, just plain old Python SymPy does it in 490, which is okay. Maxima, which is an old program, I've seen other people quoting that, people who know what they're doing, quoting that it does it a lot faster than this, but it runs on about 6 or 7 different implementations of Lisp. I chose GCL, and it just kept eating up all the memory and crashing. So, these general sort of general things that aren't made to do algebra, but rather symbolic manipulation, I want to point out that this is how they will store internally a polynomial. So this is obviously, excuse me, quite inefficient if you just want to do efficient polynomial manipulation, because I can replace that by a string, cat, or whatever I want, and the thing has to support that. So this is a partial history. Since time is, it's already partial, I'm going to abbreviate it a little bit more, but there's some instructive things here of symbolic computation systems. This was written in assembly language. This guy later got a Nobel Prize in physics. He used it for physics calculations. Reduce is still around. There's a Julia interface to this one. Maxima was sort of the big one. It was the sort of the model application of Lisp for a long time. It is a very long, it's a soap opera, the story of Maxima, that I won't go into, but it was a victim of circumstances and sort of died in 1992. An open source version persisted. William Shelter continued to develop it and got permission from the DOE to release it under the GPL in 1998. And some of the original Maxima people like Feitman and Stavros Makrakis are still working on that and so forth. Maple started around the same time. These things, so it became clear around this time that C might be a good choice to write the course. So they started doing things in C. And they all have this algo-like language. Maple actually says it's Pascal-like because they don't want to be too old-fashioned, so it's Pascal-like rather than algo-like. SMP was by Cole, and this is Wolfram's first effort, but it already had a lot of the stuff that Mathematica had in it. A lot of the ideas, this sort of obsession with making sure things were expressions. Everything was an expression. And largely the pattern matching that Mathematica has now was put in place there. And I've seen Mike Innes debate with other people whether you should use underscores or dollar signs for the patterns. SMP used dollar signs, and for Mathematica they switched to underscores for what that's worth. And so then Mathematica came around. And one thing I want to, people debate about why did Mathematica succeed and these others didn't. Somebody had better numerics, somebody didn't. Mathematica was above all a product. Wolfram wanted to win. He had organizational focus. The thing was designed very carefully. He buddied up with Steve Jobs. They had a marketing blitz. I mean, it was a product. The other things were really interesting math projects that people, wanted to commercialize a little bit. And that's why this succeeded. This is just, my opinion for what it's worth. But I think other people share it. MuPad, I don't want to talk about that. That was bought and is now internalized by MATLAB. Sage Math, I'll talk about a little bit later. William Stein wanted to take all of these things and put them together and tie them together with Python. SymPy started in 2006. And this is pure Python. It's now trying to be completely expression-based, but it also, all of the documentation and all of the tutorials and everything are riddled with classes and hierarchies and instances and so forth. So you're expected to be a Python programmer to use this. Mathix is a front end to this, which is sort of a Mathematica clone, which is interesting. I don't know if I'll have time to get to why. And then Samata is the thing. So this is the culmination of all of this history, is Samata, my package. I also want it to be very expression-based and expression-based language because I want to avoid this pudding has no theme thing. Let me throw this and that. I want it to have a theme, but for various reasons, I think it needs to have a layer where you can break through that, get under that. Part of the reason being with over 30 years and hundreds of millions of dollars, Mathematica is still slow because they refuse to break that fourth wall and maintain this fiction that everything is an expression. And then these were some of the things I worked on earlier before getting there. So why are there no competitors? I don't have time to go into this too much either, although it's a very interesting question. William Stein said, well, he said, this is what a lot of people say. He said, it was almost like what other scientists say. Magma is the only piece of proprietary software on my machines. I've said that about Mathematica. Other people have said that. Why? I don't have answers. I'm asking the question here. There's some possible reasons. One thing that I've told people, and people have argued me and say, no, this is not true. If you want all of this stuff in Julia tomorrow, get CRUD working on Julia today. If you capture 0.5% of the CRUD market, and whoever, Facebook, wants to run a little faster, they'll throw $1 million at it to get it to run faster. This is just an idea. Okay. Development models or modes. Academy only cares about publications. A mediocre paper is better than great software. Yesterday, or the day before, Alan Edelman said that's changing. So I don't know, maybe it is. Sage Math, so Stein left academia recently and decided to do a company. Here is a counterexample. William Hart, who wrote, this is another interesting thing. He's been obsessed for years with writing the fastest algebra code. For algebraists that he can. He wrote Flint, and he's benchmarking everything. He's always written everything in pure C. Somebody else can write a C++ wrapper if they want. He wants speed. He's recently started writing stuff in Julia. It's the only other language I've seen him use. And there's a big grant. It's called Massive. I couldn't find the amount of money, but to try to put these things together to make a competitor to Magma. So Germany is at least saying, no, it's in our interest to try and do something like this. Whoops. So I've already talked a little bit about this, what that is. So here's, again, where am I at now? Okay. I don't have time to talk about a lot of these, but this is just a list of, and this is another interesting thing. You can look at Rust or Go or whatever you want. Some people are trying to do some symbolic things, some numeric things. This is a partial list of the symbolic and algebraic things people are trying to do with Julia. There's a lot. I mentioned this. This is the fastest. Nemo, he's using to wrap some of his other old Flint, his older packages. And for some reason, I tried to do those benchmarks with Flint, which he claims is the fastest. And I think maybe the translation is not fast enough yet or something, but the pure Julia was faster. These are wrappers are for some other things. Algebraic numbers is something that I find very interesting that hasn't attracted a lot of attention, but that could be very useful in things like Samata or Mathematica-like things. Blah, blah, blah. These are two popular polynomial packages. And this one actually represents things in a pretty efficient way, and you saw that it did that manipulation rather slowly. So that's something the authors of that could look at. I'm sure that could be improved. And these are general purpose programs. So, and I'll just show a little bit. Okay, so why did I do this? I've been sort of messing around trying to help pushing Maxima stuff for a lot of years, doing things in Common Lisp. Within a month of learning Julia, I started doing this. A big thing is it's not just that I can use what Julia has, but I can repurpose it. Symbols and expressions, syntactic macros, these things are all at the top of the language. I didn't write a parser. I just reinterpret the ST. The parser is done. That's a huge, huge job. I/O, Julia gets you access to what they use to read source code. I can read source code and find an error and print a line number. It's this much code. I mean, in C, Common Lisp, God knows, you know, this is a huge amount of help. High performance data structures, generic methods, this is stuff we all know about. I hijack the REPL. I write a REPL mode. You get multi-line editing, history. I can stuff the user's symbols that they enter into the completion thing. You know, Maxima under GCL only has command line completion, and it doesn't complete Maxima. It completes the old Lisp symbols all in caps, like it was the mid-'70s. So, you know, people there aren't thinking about this stuff, but I want something that people can use and people want to use, and you have to have this stuff. In fact, nobody wants this. They want Jupyter, right? So you have to have Jupyter. It has these great language interfaces. You know, you have to have a good interface to Python and C to make this work. Python has all of this. I mean, SymPy is fantastic, and so on. And the community cares about all this stuff, and they understand all this stuff, which for software devs is kind of obvious, but not if you look at these older symbolic projects. The people there sometimes are not as forward-thinking. So Samata, as I already said, everything's an expression. It has a tight design. I inherited a lot, or copied a lot of this from Mathematica. I won't say a lot about this. I use the same so-called evaluation sequence where you descend into an expression, you evaluate things a certain way, you apply the internal rules at a certain time, then you apply the user-defined rules, et cetera, et cetera. And I found that when I deviated a little bit from that, things didn't work as well, which made me think Mathematica is actually pretty well designed. Pattern matching plays a central role. And there's this Ruby thing, which I can talk about later, which is the best integrator in the world, which is all based on Mathematica rules. Yeah, I won't talk too much about this. They use the word orderless for commutative, and I copied that, and flat for associative. And the reason is because they want to emphasize structure over mathematics. And Wolfram did this way back when explicitly. These are some of the elements of the pattern matching. I won't talk about those. I don't have time. Here's some related things in Julia, this rewrite package which does rules. And macro tools has a different purpose, but actually does some similar things. And so now I'm only going to show a little bit about what Samata does, because basically what I'll be showing you is Mathematica with a slightly different syntax. So you can go look at Mathematica. But here's an example. And you can compare this to the SymPy code, which runs a little faster because this is not optimized. But this does angle addition expansion everywhere in any expression for sine and cosine. So here's a rule that replaces sine of the addition of two things with this expression, and the cosine of addition of two things with this expression. And this will capture one term, and this will capture all the remaining terms. And then I put a plus back on that because it's splatted, and put it in the sign. And then this operator is replace repeated, which goes over the expression at all depths until it stops changing. And so I stick this in it, which has sine not at the top level, but at one level down, and it expands it. It's not super fast, but you can, I mean, I'd rather optimize this guy here than write a lot of optimized code for each one of these. So this is the way Mathematica started at the beginning. They wrote everything this way with the core in C, and then went by over the years optimizing the things. So this is what the rules do, and this is why it's based on rules. So what I do want to, with the remaining time, focus on is the stuff that is unique, or that you do get in Samata that you don't get in Mathematica, which is, so Wolfram intentionally makes this, the fourth wall impenetrable. Everything's an expression you can't see within it. And people know that he stores the certain kinds of rules in a hash table, but if you ask for them, he'll give you this huge list of rules written in this pattern syntax. I don't know if it's useful, but everything that's presented to you is patterns and rules and expressions. So this is what I chose. This J just means whatever is in here, interpret as Julia. So this gets the Julia time function, and this calls it. This is a Samata prompt, and I get time. So you can get access to all the Julia immediately that way. That's a pretty easy Julia and C interface. Here's an example. These are two, this is a range of floating point numbers between 1 and 1,000, and this is the same between 1 and 1,000. And this looks just like a Mathematica function. I do a loop, I square the elements here, cube the elements here, and that's actually, that should be a plus there. I think in the end I did make that a plus. It doesn't matter. So one thing I can do is feed them here to square the elements here and divide them by the elements here and sum them. Or I can, this has the old Julia, a way of squaring an entire array and dividing it by an entire array, and that could be changed or not. And then you apply plus to it rather than list, replaces the symbol list with plus, sends it through the evaluator and adds it. Or this is a pure Julia function. This is generic Julia, so you can read this just like a Julia function because it is. It zips these first two inputs and then loops over them, and the sum function takes a function and applies it to every element of what's here. And this does the same thing. And these are the timings. If this is normalized to 1 to do this operation, apply sum takes 1/2, and using the Julia function, which is easy to write, it's 1/20, which looks fast. I had a performance regression since 0.05. This used to be 500, so maybe I can get it faster. But this is nice because I can sort of break this, get around this if it's too slow for me and get something a lot faster using generic Julia code. And that's not all. This is a copy of the exact same generic function, and now I pass it to symbolic expressions, and this is what it gives me back at Jupiter. The reason is that these are, I call them M expressions, and addition and division and so forth are overloaded for those. So I can automatically call this on other expressions, which is something that you're used to seeing in Julia, but other people might go, well, how'd you do that? I didn't do anything. I didn't do anything. So here's an example with a little bit more of the, to show you a little bit of the sort of the symbolic, the Mathematica-like side that does. And this is due to SymPy. Integrate this expression with respect to x, and then factor out e to the x. And this is handed off to SymPy, which hands me the answer. And SymPy is great. It's very complete. And this is the expression I get. And here I say compile it to a Julia expression, because this comes back as a Samata purely symbolic expression. And I say this is the parameter x. And then here is just a copy of it. I didn't put the prompts here. This is Samata. This is a Samata expression. This is Julia. This is pure Julia. I did just copy this by hand and say, let me make an efficient Julia function that does this. And then I used benchmark with 2.0. And this compiled expression runs in exactly the same time as the hand-coded Julia does. So this is as efficient as it can get. Then the other thing you can do is, instead of putting in this number, put in a symbol at the Julia prompt, and you get back a Samata expression because it's generic. And the reason being, it's down here. I translate power to m power. This I took from maxima, plus to m plus, and so forth. And these are overloaded. If you get a floating point number, it calls the Julia floating point thing. If you get other objects, it calls other objects to construct a Samata object. And then this is another, there's a few more examples of how to get, if there's something you can't compile because it's not written yet, this essentially makes a callback to Samata. So this could be an arbitrary Samata expression. And inside of Julia, I call that. It makes a wrapper around that, makes a substitution, runs it through the Samata evaluation sequence, and gives me the answer back in Julian. So this is another way to get around the efficiency problem to a certain extent. And hopefully, This was me just praising SymPy. They did not try to optimize it at all, which is, I think, the way to go. And so rather than getting 10 or 15% of they wanted very fast, they got something that's fast enough for a lot of cases. It has a whole lot of what you want in an algebra project. So I think the SymPy people did a great job. I don't know what they're going to do now. And then the other fault from my point of view is that you're not going to get a lot of people to use it if you force them to think about objects too much. And this was the last thing. Why would I want to do this? When do people want to use this? And I've been talking to people here. Why do you use Mathematica and why do you not? I mean, I used to program in it sometimes, but now I go there because it's complete in certain domains. If I need to do an inverse Laplace transform and I need to do some special functions that are a bit exotic, that aren't in the GNU Scientific Library, I need them to high precision, complex numbers. Mathematica is going to have all that covered. It's the only place I know to go. And I talked to Jesse, I talked to other people who said, yeah, they knew other people who go there just for that reason, that they know it's going to cover their domain. That's something, you know, I'm not getting with this project. So that's something to think about. And anyway, there's other things to think about. But I think this is a good question to ask when you're doing any project like a Julia project is, you know, who do I expect to use this and when? And so that's it. Thank you.
Thank you, John, for your very interesting talk. Do we have any questions?
It seems like Julia should be a good place to actually write a symbolic manipulation package rather than using SymPy.
Yeah, okay, and so this, in my, what I want to do is absolutely, I don't want to touch and replace any SymPy unless I can replace it all, because SymPy and Python are now a dependency, and to me, it's a waste of development effort to say, Julia is better than SymPy, let me replace this little piece. SymPy is allowing me to develop an entire tool that's useful, and then, you know, when that's in place, I don't know if you see my point.
Yeah.
And I agree with you 100%. It is, and it would be really nice to, and it was so tempting, and it was Francesco Bonazzi who kept telling me, use SymPy, use SymPy. And I want to use Julia, and then his suggestion was correct. But you're absolutely right. I mean, I even did some of this, and if I played around with expand, say, or a lot of these functions, and of course it blows SymPy away. And it's a very good language for doing that. And it's better than SymPy. Or Python. Python is a horrible language to try to do this in. You go through their code and try and look at their, Julia allows you to naturally code with this flat structure. I want to do that, but you know, I have a day job and so forth. If any of you guys want to do that. But your point is very well taken. It would be great to be able to get rid of the Python, but I'm glad SymPy is there. So, yeah.
Yes, thank you for this great package. I have a question about this capital letters for all the function calls. Was this necessary because you want distinguishing from normal Julia code, or was this because of Mathematica or something else?
I followed Mathematica, and this is part of a general question. How slavishly do you want to stick to Mathematica? Because if you break from it too much, you lose compatibility in terms of translating code. I stuck to it for two reasons. One is because it's just what Mathematica uses, but it's very nice. It's a nice way of making this user versus language space distinction. I mean, their rule is you can always safely use anything with lowercase, never start something with uppercase. So that's why I did it. And actually, after using Mathematica for a while, I like it. But it's not at this point, it's just something I stuck with. I mean, I don't know, do you have a particular opinion on that, or is it a...
Yes, but it does not matter.
Yeah, the answer is I've stuck with it for the time being, but it's not set in stone.
But then you can't use generic Julia functions.
You can't get what?
You cannot use generic Julia functions.
So you saw I used that capital J. So yeah, I mean, it's like this. Where was an example? I just bind it. Now these happen to be, see this Julia sum here. I happen to give this a lowercase here because I want this to be a user space thing. This is a Julia function, and it returns, I don't know, the compiler people here could tell me, is it a pointer? Whatever. It returns the Julia function, binds it to a Samata symbol. Now, if I want this to be core Samata, I just put a capital letter there. I don't know if you, this is Julia syntax, and that's actually a Julia function. And this J thing says construct, compile the Julia function, come back up to Samata, and bind it to the Samata symbol.
But the question is, can I use my generic Julia code without changing anything and put a Samata object in? That's what
I see. You know, I meant to write that and I didn't. There are several ways to do that. So this stuff is done via a macro that's interpreted, and there's one macro that's, you know, ampersand sim. And that interprets everything as Samata code. And that's, I really wish I had done that. Yes, you can do all the reverse. You can be writing Julia code, and by using the sim macro, it interprets that as Samata, and whatever it returns then comes into Julia. If it happens to be a Samata expression, you get this type called MXPR, which is like expression, which are parameterized by the head, like plus or something, or it will return, if it returns a number or something, it returns a number. But no, this is designed to use it from within Julia. Part of the reason is for efficiency. And Rob Goodman, I didn't know he would do this, but he uses this, and he uses it entirely that way. He never uses a command line. He always uses it from within Julia.
Okay, well, we're over time, so thank you very much for your talk again. I'm sure lots of people find you afterwards for more questions because it seems very interesting. So.
Thanks very much, because that's something that I kept saying.